Welcome to our final project presentation. This is Patrick.
This is Levi.
Our topic is a painting style classification and transformation. And first, let me introduce you to the problem. In 2018, over 7 million people have visited an art exhibition in Shanghai. People are nowadays very willing to purchase for an art style. For example, this kind of bookmarks were sold over 30,000 pieces in only one Taobao store last year. However, not everyone has ability to identify the art style, and not everyone has ability to paint under the same style with the content he wants. So we help people classify the art style and even help them create another one under the same style. So the data set we use is from Kaggle, which is a professional data website for machine learning studies. And our main data set is best art of all time. It includes over 8,000 paintings of different styles, eras with full labels, and we identify this as a strong enough database for us to learn. So let me introduce Levi to introduce you some details about the data process.
Okay, the graph on the left shows the original data distribution over 21 different styles. And as you can see, this data set is imbalanced. For example, Impressionism contains over 1,000 paintings, while pop art contains only less than 100 paintings. Such an imbalanced data set will be harmful to the performance of our model. Therefore, we follow 5 principles listed on the right to make it balanced. First, we abandon all styles that contain less than 150 paintings and also merge similar styles into one class. And second, for those cross-style paintings, we only put them into one style. And third, because there are few monochromatic paintings in the dataset, in order to avoid overfitting them, we abandon them all. And next, we randomly choose 500 paintings from each style. If there are not that many paintings in that style, we do data augmentation by randomly flipping some paintings horizontally or vertically. And last, we resize each painting to the size of 1:8 times 1:8. Now, get a balanced data set with 500 paintings in each style. Now, we also reduce 21 styles down to 14 styles. And then we allocate different portion of paintings from each style to our training, validation, and test sets. And then the configuration of our training, validation, and test sets are listed on the right. Okay, now let's look at the structure of a model. We first do transfer learning. We put our 3 sets through pre-trained AlexNet to get the data representation. And then we put those data representation through our self-defined fully connected layer to reduce the dimension from 1,000 to 14. Note that here between the first hidden layer and the second hidden layer, we also use dropout regularization to avoid overfitting by randomly activating some hidden units. And then other configurations of the model are listed below.
Now let me introduce you to the style transfer. We use the neural style algorithm used by some scholars from Cornell University. In general, it measures 2 distances. First is the content distance between the input data and the content data. Second is the style distance between the input data and the style data. Then the algorithm just adjusts the input to minimize the 2 distances to get the result. So we use a pre-trained neural network, VGG19. Different from VGG16, it uses 19 layers, and which is more powerful in this case. It gives very strong presentation of our images. And here I want to talk about our training process. We use the MSE loss function, and we set up our maximum step at 300. And here I want to emphasize on the gradient descent optimizer. We use the LBFGS algorithm. Different from Adam, if you remember, in Adam, we are kind of like averaging the gradients directly. But in LBFGS, we're looking at the second derivative. And here you can see how good it is. Like in Adam, under 300 steps, we can like barely get like close to the style loss. But for the LBFGS, we can reduce the style loss very fast. So in LBFGS, we're looking at the second derivative, which is kind of a guidance for us to like move gradient faster and smarter. And in this case, it works extremely well. And so let us discuss about some results of our project. For the classifier, we get our accuracy of prediction around 50%. And for the style transfer, we can reduce the loss, so-called distance, to 1 to 10%, and we can finish the transfer process within only 1 minute. So let's have a look.
With the original imbalanced dataset, the accuracy was around 15%. After data pre-processed and network optimization, such as transfer learning or dropout regularization, our final test accuracy increases and is around 50%. This is not very high result, but it could be further improved by considering some potential issues to be discussed later.
So now let's put together the classifier and the converter to realize the use case we mentioned at the very beginning. So a visitor can now just take a picture when he's like in the museum, and he can put into the classifier. Like in this case, it will tell you that it's impressionism of Van Gogh's painting. Now you can put into your own picture like here, and you just run the converter and you can get the new painting, same style and under the same content. And here, like I just make my own bookmark, and you can just show off to your friends via WeChat or via Instagram. So let's bring some discussion to our project. For the classifier, as we say, the accuracy is around 50%. It's not that high, but it turns out can be a very good supporter to give the visitor some options for the style classification. So for example, we can give the visitor some choices. I give them the top 3 highest possible styles and let them to choose. But there are still some issues we can figure out and to improve our model. And for the converter, it works well in general, but it might have some problem if the input image is too far away from the style image. So now let's Levi to tell you some issues.
Here are 4 major issues of our model needing to be further improved. First, it never hurts to get more training data. And second, since our computer is not that powerful enough, we cannot use larger image size or larger network like VGG19 to do data classification. And third, for those cross-style paintings, like the one on the upper right, it's difficult for our model to tell them clearly and precisely. And last, when we resize the paintings, the shape changes a lot, like the one on the lower right. This entails that the information within one painting is twisted terribly. Therefore, if we have more time, we'll further work on those issues to improve the performance of our model.
So here we want to end our project by showing you an interest approach we did. So we want to realize a function that we can take on the mask and take off the mask by using the similar algorithm. So we need to get some style data first. So we get our database from Kaggle and use the COVID-19 mask detection database to generate the face with the mask and without the mask like this. And then we can just convert the input picture with the mask to without the mask. And then to the without mask to without the mask to with the mask. But as you can see here, even you can see the approach, but it's not very satisfying for the result. So as Levi just said, if we have a better GPU or better spaces, we can use larger models or greater models like GANs for the converter and VGG19 for the classifier. And if we have more time, we can explore more databases to move it to larger databases as we have right now. So thank you for listening. Thank you for watching our project. Thank you. Have a nice day.
Thank you very much.